electron configurations, which are one of the harder things that we will do that is not math related, really. It's kind of math related in the sense of there's numbers involved in it, but you don't have to do any math. So if you haven't gotten to this lesson yet in Canvas, that's totally fine, right? I'm going to explain sort of the background behind electron configuration, what it is and how it works, and then we're going to talk about a shortcut for figuring this out. The lesson in Canvas tells you a different way to do this, which is also fine, right? There's many ways to correctly do this. You guys are sort of at an advantage here because you don't have to memorize this necessarily, right? Because when you take your test, you will be able to use your notes. So I recommend that you use this time to make sure you have all the notes written down that you could possibly need to be able to successfully do this, so that when you are taking a test, you have access to those and you're not trying to recall something that I said in this virtual session. So, electron configuration. Today's objectives are: identify how electrons behave in their energy shells, write electron configurations for some elements, essentially by learning the shortcut to do this. And then we probably won't have time to do this final objective with valence electrons. I sort of added it on at the end here. I think I will move that to next week's virtual session, but if we do have time, we'll go over that. So here is our warm-up question for today. A quote that I took from the Florida virtual lesson on electron configuration. All systems in nature tend to take a position or arrangement that has the lowest possible potential energy. So right now, I want you to think about what that quote actually means and try to give an example of maybe a situation that you think represents that, or a scenario that you think represents that. So I'm going to give you guys about a minute and a half right now to reword this quote into your own words and think of an example.
Just a moment.
By the way, when you think of how to reword this, you can go ahead and pop your answer into the chat, right? If you'd like to speak out loud, you also can totally do that if that's easier for you. But at least be writing something down so you have an idea of what this quote is meaning to you. All right, so I'm not really seeing anyone's writing here. Okay, thank you, Bella. Yeah, one person. And Logan. Okay, good. You guys are just waiting patiently. I love it. So systems in nature usually put themselves in a position that doesn't give them as much stored energy. Okay. Things will try and be in a spot where they'll have the least potential energy. An example of this is gravity. Gravity is a great example, right? In the sense that things that are higher up above Earth have a greater potential energy, right? And if there's nothing holding them there, they will fall closer to Earth. Can you guys all hear me okay? Because I know there's a lot of noise in this room. If you can give me a thumbs up or a yeah. Okay, good. Because I know I'm really loud, so, you know, shouldn't be a problem, but you never know. So great, gravity is a great example of that. Today, we're really going to be looking at electrons as an example of this, right? You might also think of this concept of entropy, which you may have heard about in other science classes, which is that everything tends towards chaos, essentially. You may notice this even in your room, right? If you're not constantly cleaning and organizing your room, what happens to your room? It gets messy, right? That's actually a natural thing. You can use that in any arguments that you want to have with your parents about why you shouldn't have to clean your room, because it will just become disorganized again based on science, which is true, right? But still, organizing can be a useful thing too. But really, that's another example that's more like a real life example that you probably have experienced yourself. So, what do electrons want? Exactly. Why is your room so messy? Chaos theory. Exact, perfect answer. Right? In fact, if you want to use the science word, it is entropy is the scientific explanation of that. So what do electrons want? Now notice I put want in quotation marks because electrons don't actually have feelings, right, or opinions or desires necessarily. But what do we know about how they behave and what they do? Well, it turns out that they're actually really sneaky and pretty hard to understand. So we basically don't understand anything about them, but this is what we do know. They want to be in the lowest energy level possible, right? What does that mean? They want to be as close to the nucleus as possible. Why would an electron want to be close to the nucleus? What is in the nucleus that an electron would desire or want to be near? An opposite charge, perfect, protons. Right? Protons are in the nucleus. They are a positive charge. Electrons want to be as close to that charge as possible. However, they don't want to be near other electrons, right? They are negative charge. Other electrons are a negative charge. They want to get as close to the protons as possible without being near other electrons. As you can imagine, kind of a difficult thing to do, right? Imagine that you're going to a family barbecue and you want to be as close to the food as possible, but you don't want to have to talk to anyone in your family. Pretty difficult feat, right? Maybe you can constantly be eating so that you can sort of move away. But it's hard, right? Everybody is going to want to be near that food. And then, of course, they're going to be near you. Oh, how are you? What are you doing? How's school? Blah, 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 right? So electrons feel the same way, essentially. The arrangement that the electrons actually form is going to determine the properties and the actions of the atom. So you guys have already kind of seen some of that stuff with when you started talking about, what am I thinking of here? The flame test lab, for those of you who've done that one, the virtual lab, right? The way that different colors actually got expressed was based on electrons. That's why different elements have different colors, because they have different arrangements of electrons, they have different numbers of protons, right? They have different orientations. So each atom of an element, right, is different from other atoms. It's the same as atoms from that same element, right? But sodium and potassium, for example, are going to be different in the way that their electrons are organized and arranged. To some extent, right? There are rules, which we'll talk about right now. So how can electrons basically get everything they want? How can they be close to the protons, but not near each other, right? And then give atoms these properties. Well, they do something that's called configuring, right? And there are several levels to this configuration. They are called S, P, D, and F. I'm not going to go into extreme detail on, how these were discovered and exactly what they mean and all of that. You guys can check out the Canvas lesson for probably more detail than you ever want on that. But we're going to talk a little bit about what these orbitals look like, how they sort of get filled with electrons, and then how we can actually write out an electron configuration, which would tell us how many electrons are in each energy level, essentially. So S, P, D, and F are basically energy shells, right? They are describing a type of configuration, and we're going to have multiple levels of them. Another thing that we need to know is that electrons can actually form a pair, right? So they spin in a certain direction, an electron. And if an electron is next to it that's spinning in the opposite direction, that's fine. If electrons are spinning in the same direction, they definitely don't want to be near each other, right? So if they have opposite spins, they can actually pair up. And a lot of times when we talk about valence electrons or electrons generally, you may have heard about them obviously before this class, we talk about them in pairs or we draw them in pairs, right? That is a thing they do. They do pair up if they have opposite spins. So that's important to think about as well, right? If they're spinning in an opposite direction, they're totally chill with being near each other. Again, a weird thing. So what do these orbitals actually look like, right? These s, p, d, and f orbitals. Well, here is the three-dimensional structural geometry, right? S orbital is just like a giant circle. The p orbital is like a figure eight of two circles being met in the middle. The nucleus would be right in the center of all of the x, y, and z plane here. D orbital is sort of like two p orbitals together. And the f orbital is just like balloons, right? It's a bunch of different stuff happening. So electrons will fill these orbitals in a specific order. S is going to have the lowest energy because it's going to be the closest to the nucleus. But again, only so many electrons can go into an s orbital, right? Specifically, 2. Not very many. Right, the p orbitals can hold 6 electrons. And I say orbitals because there are more than one p orbital, right? They're going to be even further and further away from the nucleus as we go up. But p orbitals can hold 6 electrons, d orbitals can hold 10, and f can hold 14. Which kind of makes sense because we see here s orbital looks the smallest, right? It's just a circle, and f is like all this craziness going on. Makes sense that an f orbital would be able to hold more electrons, right, than in an s orbital. Again, these letters, s, p, d, and f, are just describing which orbital the electrons are in. Okay, so far, hopefully so good. I know this is a lot. Once we talk about the shortcut, hopefully it will become a little bit easier to kind of understand what we're talking about here, but this stuff is pretty intense. So what about 32, as in if we had 32 electrons, Logan? Is that what you're asking? I'm assuming, I don't know if that's what you're asking, but you'll see there are many s orbitals, many p, many d, many f. So we can actually go all the way through every single element in the periodic table. So we can go up to like 200 and whatever electrons there are. We'll just have a first S level, a second S level, a third S level, a fourth S level, right? So we have multiple versions of each one of these so that this can expand to encompass all electrons. But again, the more electrons you have, the more layers you're going to have of the atom, right? Because they can't all be close to the nucleus, so you're going to start going bigger and bigger and bigger and bigger. So there is an orbital level. You thought the maximum element was 137. Actually, that is a good question. What is the biggest one on the periodic table? It might be even less than that, actually. 111 is on this periodic table that I have here, but the biggest one discovered is 118. Yeah, so exactly, right? But even if we had up to 200 electrons, we could still figure this out with the orbitals. But you're right, the biggest element, 118, would mean 118 electrons. It's going to have s, p, d, and f orbitals, many layers of them. So this is the order that the electrons fill the orbitals. The arrows are representing the order that they go. So first, electrons will fill 1s. 1 meaning the how close it is to the nucleus, and s being the shape of the orbital. So we know from before that the s orbital can only hold 2 electrons. So that means that in this first layer of electrons, we can have 2 electrons in this layer, right? That's only going to help us for 2 elements, hydrogen and helium, because those have 1 and 2 electrons. Our second level is also an s orbital, but it's a 2s, meaning it's a little bit further away from the nucleus. Guess what? It can also hold 2 electrons. Then we have a 2p, or excuse me, yeah, then we have a 2p because you follow the way that these arrows go, which by the way, the shortcut's going to be way easier than this. In a 2p orbital, we can have 6 electrons. Again, that's just something you have to know. 6 can fit in the shape of a p orbital and be satisfied, right? Then next, we would go to 3s, right? Then we would go to 3p, then 4s, then 3d, then 4p, then 5s, then 4d, right? So we would follow the way that these arrows are drawn. Now, the most important thing I'm going to point out to you is 3d and also where these f orbitals come in, because they are sort of the weird ones. And on the shortcut, you kind of have to know that 3d comes before 4p, which is a little bit confusing. I will sort of explain that again in a second, but those are the two that you should probably be going, okay, that looks a little different in the order that we're going, right? Notice that d orbitals don't even come into play until the 3rd energy level. There's no 1d, there's no 2d. 3d is the first level where the shape of d can actually happen, right? Same with f. F cannot happen until the 4th energy level. So there is not an f orbital in the 1st energy level, right? Two different things. Again, if you're starting to get confused, because let's face it, this is confusing. Energy level is going to be represented by the number. So in this case, we have 1 through 7. And at the same time, we have our orbital shapes, which are represented by the letters. So S is the sphere, P is the figure 8 thing, D is the bigger figure 8 thing, etc. So we have 2 different pieces of information here. We have an energy level and a shape. Okay, well, we also need to know how many electrons we have. So what do these things look like? And why would we care about this, really, is probably what you're thinking. You're like, cool, this sounds fun. Electrons are crazy. They go all over the place. They have energy levels. We get it. Well, this is the shortcut. It's a periodic table shortcut. And we are going to use this pretty extensively in the rest of this virtual session. I recommend that you either take a screenshot of this picture and keep it on your computer, maybe print it out. 53 is just circled because I stole this from someone else and I think they used iodine as an example. So that's actually not important. What's important is the S, D, P, and F labelings with the circles of which elements those include, because there's going to be a shortcut that I'm going to show you where you can pick any element and you just follow the lines of the periodic table and it will tell you the electron configuration. So again, you might want to screenshot this. You might want to print it. You potentially, if you have a printed out periodic table, maybe you just want to make these distinctions on your own periodic table, but it will save you a lot of time. So how does this work? Well, how can we write this out? So let's say that we're going to do something for carbon. Nice, easy one to start with, right? If we look at carbon on the periodic table, we see that carbon has an atomic number of 6. We know that means that carbon has 6 protons, right? In a neutral atom, which we pretty much are only dealing with neutral atoms right now, we also know carbon has 6 electrons, right? Because we have to have protons and electrons equaling each other for an atom to be neutral. Okay, well, we know carbon has 6 electrons, but then the next question is, how are they oriented? How are they configured, right? Does carbon have electrons in 1s? Does it have electrons in 2d? Oh, 2d doesn't exist in 3d. Where are they, right? That's what we want to know next. Well, here is what the electron configuration for carbon looks like, and I'm going to go through how we get there. But as a chemist, right, or a science literate person, you can look at this and you can say, okay, carbon has 6 electrons. 2 of them are in the first energy level in s orbital. 2 of them are in the second energy s level or s orbital, and 2 of them are in the 2p energy level and orbital, right? So in my mind, I would now know, okay, that's how carbon's electrons are configured. So thankfully, you don't have to draw that, right? But you can visualize that there are going to be 2 spheres, one very close to the nucleus, one further away from the nucleus, as well as a figure 8 shape. And 2 electrons are going to be in each of those shapes moving around constantly, right? They don't stay still. So how do we figure this out? Well, we go back to our cheating periodic table. And this is what we do. We start with our first energy level, which, by the way, where do we get energy levels from? For the most part, it's the row. 1, 2, 3, 4, 5, 6, 7. There are 7 rows to the periodic table. Guess what? There are 7 energy levels. So far, so good. Also, this should make you a little bit freaked out at how good the periodic table is. Like, it's just amazing. It's perfect in every way, right? Which is sometimes disturbing, at least to me. Now, I'm going to put a little asterisk here next to 3 because D and F are going to have slightly different rules. Remember, D starts at the 3rd energy level. Well, I see D on the periodic table in energy level 4. So that's going to be a little bit different. We'll talk about that in a second. But I'm just going to put a little asterisk there to say basically that D and F do not follow these energy levels 100%. S and P, though, do, which is great. So all we do is we follow the periodic table until we get to the element we want, filling in how many electrons there can possibly be. And guess what? You don't even have to memorize it. Because S is 2 columns. Guess how many electrons are in S? 2. P has 6. 1, 2, 3, 4, 5, 6. 6 options. Which means there can be 6 electrons in P. D has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F has 14, right? And if you count, you will see there are 14. So you don't even have to remember how many are in each one. 71, we will get to that in a second, Logan, because I will have to check it. But basically what you do is you start off with 1s is always the first thing. Every single electron configuration is going to start with 1s. Then I come to my periodic table and I say, well, I'm going to carbon. Carbon's over here. So 1s1 would be hydrogen. 1s2 would be helium. I'm not to carbon yet, so that's definitely true. I need 2 electrons in my first energy level here, so I'm going to put a little tiny exponent to represent my electrons. 1s2 got me to helium. So now there's nothing else in this top row, right? Helium kind of gets moved over to be part of S, even though it's a noble gas, right? So I come to my second energy level and I say 2s. Well, I'm going to have to do 2s2 as well because I have to get all the way to carbon and I'm not there yet. So again, I'm going to denote that by putting a little exponent, which I know my 2's look kind of strange. It's hard to draw with my mouse finger. Then I'm going to keep going because I'm not to carbon yet. I'm coming over to my P section. Well, how many electrons do I need in P to get to carbon? 1, 2. I'm at carbon. So the final part of my electron configuration here would be 2p, which is barely showing up down here. And I would write a 2 exponent up there as well because I have 2 electrons in my p orbital in order to get to carbon. So 1s2, 2s2, 2p2 would be my electron configuration for carbon. So let's see, Logan, you just went ahead and went for like a super hard one. So let's check it. Well, the first thing I'll say is I don't see a 1s2 in your configuration, right? But you wanted to do element number 71, which is right here. So let's see. And maybe, why don't you guys write this down as we go? 1s2, for sure, we get to helium. 2s2, yes. 2p6, because I'm going to have to go all the way across 1, 2, 3, 4, 5, 6. 6 electrons in 2p. Then I'm going to go to 3s2. Then I'm going to keep going straight across the periodic table to 3p. 1, 2, 3, 4, 5, 6. Okay. Then I'm going to come to 4s2. Now, when I get to D, this is where it gets confusing. The first energy level of D is 3. So after 4s comes 3d. This is a very important thing to note. The quiz on this has a question about that, and that is the answer. They start filling a 3d orbital before 4s has been filled, and you can't do that, right? It goes to the lowest energy level available. 4s, even though it has a 4 in front of it, is technically lower energy than 3d. So that is a trick. So we would go to 3d, 10, because we go through the whole row. We're still in the 4th energy level for P, though. So D is the only one where you have to kind of go backwards one. 4p6, 5s2, 4d, 10, 5p6, 6s2. Basically, I'm just checking Logan's right now. We're going to practice this a lot, so don't worry. Here, though, I see these stars that take me down to actually my first F orbital. Now, you may remember, though, F, the first level of F was actually a 5. So D and F are always going to be 1 less than your energy levels for S and P. So then you would actually have 5F14. And then finally you would get to 5D. No, excuse me, I think it's 4F actually. 4F is the first one. F always confuses me because I never make you guys go this far on the periodic table. I will check in 1 second. And you will end with 5D1 because you stop right here on 71. So Logan, hopefully that helped you. If you're confused otherwise, don't worry, we're going to do more practicing. So again, remember this picture that I showed you of how the orbitals get filled. Oh yeah, so it is 4F, I was right. So the first F energy level is a 4, and the second one is a 5. There's no 6F, there's no 7F, right? There's no 7D. So on your periodic table, it might be helpful to write in your D section, right, that this is a 3D, this is a 4D, this is a 5D, and this is a 6D. And it might be helpful to write next to your Fs that this is a 4F and this is a 5F. 6F and 7F don't exist, right? But if you only go off of the rows, you will get that confused. And again, it just has to do with how the electrons fill the orbitals, right? So they fill in these orders because that's the lowest of least energy to greatest energy. Okay. Type a 1 in the chat if you are like feeling okay so far. You think this seems hard, but I'm understanding. Type a 2 in the chat if you're like, this is another language. What the heck are you talking about? Okay, we got 1s. That's good. Because I know the first time you hear this, it's a little bit like, what is going on, right? 1.5, yeah. Hey, 1.5 is a fair place to be. I'll tell you that. So I'm going to erase all my little writings here. We're going to do some more practicing. But again, make sure that you have your periodic table screenshotted with these S, P, D, and Fs labeled, right? And I would personally have this picture saved as well. So Logan's asking a clarifying question. F is 1 less than D, yes. D is 1 less than P, yes. P is 1 less than S, no. P and S are always going to be on the same energy level. Like it would be 1S, there's no 1P. 2S, 2P. 3S, 3P. 4S, 4P. So S and P are always going to be on the same energy level in order from S to P, S to P, S to P. D and F are the only ones that require you to do a little bit of subtracting. And again, that's just because that's how they fit in energy-wise. So again, S's and P's, you're just going to go by row in the periodic table. Row 1, row 2, row 3, row 4, 5, 6, 7. D starts with a 3. 3D, 4D. And in fact, it's easy to remember because it's like a 3D film, right? 3D, 4D, 5D, 6D. And F starts in the 4th energy level, 4F, 5F. By the way, if you didn't know this, right, these little asterisks here on a periodic table, yes, perfect correction there, Logan. That means that F actually gets inserted into the periodic table right here. So the periodic table is actually really, really long if you see a real fully extended one, right? Usually these 2 rows here are rarely talked about. You kind of learn about them very generally. You probably won't be doing a lot of electron configuration that requires F, right? You might. I think there's like one question with it, but for the most part, we're going to be caring about elements that are higher up in the periodic table that we talk about more, right? Because we don't usually talk about pretty much anything over here, except maybe uranium. So let's try. All right, you guys, I want you to pick. I'm going to do one of these 4 as an example. So if I were you, I would be looking on the periodic table. I would probably try to pick which one you think is going to be the hardest. And if you don't care, then just pick one. So which one of these 4 do you want me to try to do with you? And then you're going to do one. Is gold the hardest? Yes. It technically should be. Okay, so Logan says, let's do gold. Anybody else have an opinion? Gold is okay with everyone? You want me to do a different one? Okay, yeah. All right, cool. Okay, gold is hardest question mark. Yeah, it is technically because it has the most electrons, right? Which here we're probably thinking more electrons means harder configuration, which is true, right? Because then you have more stuff to write. So let's go to gold on our periodic table. First of all, where is gold? $79, awesome. So gold, remember, has a weird abbreviation, AU, right? It comes from Latin, not English. Exactly, Logan. So we see AU here, and we might not think it's gold, but it is, right? That's gold. Again, gold is written in the tiniest font possible, right above 79. So gold has 79 electrons and 79 protons. So let's configure our gold. So we're going to start with 1s. Why? Because that's what we start with every single one. 1s is our first energy level and orbital, and we are going to have 2 electrons in 1s because we only get to helium and we're not done. So 1s2 is to start. Then we go all the way across, there's nothing else. Second energy level, 2s, 2. Then we keep going across, we see that we actually have a 2p. 2p, we're going to have 6 electrons, 1, 2, 3, 4, 5, 6. That gets us all the way through the second row. Awesome, Logan. You can be checking what you did there as we go through this. Then we're going to come to our third energy level for another S, right? 3s, 2. Why? Because we're now to magnesium. We got to keep going. By the way, magnesium, I think, was one of the ones on there, so you just wrote the configuration for that. We keep going across 2p. We are still in 3, right? We are now having 3p. Do we have 6 electrons here? We do. 1, 2, 3, 4, 5, 6, getting us all the way through our third row. We come to row 4, where we have 4s, also 2, because again, we're going to fill that entire orbital. We keep going across, and we get to D. And then this is where we think, what is our first D orbital? Well, it's not 4. We wish it was, because then this would be even easier, right? But we know 3D is our first D orbital. Again, I personally would write a little tiny 3 here to remind myself that, right? But again, eventually you'll just remember it. Freakishly, you'll know this later in your life, and you'll be like, why do I know how to do this? But 3D, are we going to have to fill this entire 3D orbital? Well, we are, because gold is all the way down at 79. So if we couldn't remember how many electrons there were, we could count, excuse me, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3D 10. Then we're going to keep going across. We're back in P now, but P, we are in the 4th energy level, right? D is the only one that comes down. P, we're still in the 4th row. And again, we're going to have to fill this entire P orbital, 1, 2, 3, 4, 5, 6. So we are going to have 4p6. Then we go to our next row. Oh, so many, right? Why does gold have so many electrons? We are now in row 5, where we see 5s2 is completely filled. We're going across. We're now in D again. However, we're in 4D, right? Because we're in the next energy level for D. 4D, are we going to have a full orbital here? We are, because we're still not to gold. So we could count, right? But I happen to just remember, because we just did it, there are 10 electrons in D. I'm back to P. However, in P, I now am back into 5 as my energy level. So confusing. Really, it's just the D's that are confusing. But I'm going to have 5p, and my P is going to be full. 1, 2, 3, 4, 5, 6. 5p6. Almost there. Finally getting to the row gold is in, right? 6. You missed a layer. See, good. Now, I'm glad you're checking this as you go. We're in 6 now. 6s2, because we're going to need to fill both of our s electrons here. Then we get to the weird asterisk, which tells us to come down to F. What is the first energy level for F? Maybe I don't remember. Hopefully you wrote it down on your periodic table. But our first F energy level is going to be a 4. So we are at 4F right now, and guess what? We're going to have to go all the way across, because gold is still not, we're still not to gold. So we're going to have 4F, 14. Let's say we couldn't remember. You count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, that gets us all the way to LU here. And now we're finally close to gold. Right, but what D level is this? Because I'm confused, right? We know it's not 6. It's 5. We could always count 3rd, 4th, 5th. So we're going to be 5D. Now, are we a full shell? Not quite. We're going to count till we get to gold. 1, 2, 3, 4, 5, 6, 7, 8, 9. 5D9. So, if we go through the entire thing, we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d9. That's the electron configuration for gold. Now you guys are going to try. For which one do you guys want to do? You want to do oxygen, chlorine, or magnesium? Oxygen. All right, Logan's going to do magnesium. You can choose We're going to go over just one to save time here, but you choose from oxygen, chlorine, or magnesium and try to do your electron configuration. I'm going to go back to our little periodic table here. Your choices: oxygen, magnesium, or what was the other choice? Chlorine. Rare. So choosing one of those, I'm going to be quiet for about a minute, letting you try to write out the configuration. Okay, good. Logan's already done with magnesium. Hasn't quite been a minute. But what I will say, guys, is after gold, these should all seem super easy because there's just way less electrons. Okay, awesome. So Logan just gave us the correct configuration for magnesium. 1s2, 2s2, 2p6, 3s2 will land us right on magnesium. Oliver gave us the perfect configuration for oxygen. 1s2, 2s2, 2p, 1, 2, 3, 4, 2p4. Right? Chlorine, 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5, 3p5. Perfect. Right? So pretty much as long as you are doing any element with less than 20 electrons, it's pretty self-explanatory. Excellent job, Bella. That's exactly for oxygen. That's a perfect configuration. Okay, good. I feel like people are kind of getting it, right? The shortcut really helps, honestly. When you see Canvas, when you see the lesson in there, I remember last year people were literally like, I don't know how to do this, right? But the shortcut makes it seem doable, right? Use the periodic table to help you. Make sure you have D and F labeled because those are really the only tricky ones. Otherwise, you just follow the periodic table and it will tell you exactly what the configuration is. Okay, so there is another shortcut, a shortcut to the shortcut. It's called the noble gas shortcut or noble gas notation. So really, all you have to do for a noble gas notation is that you can find the noble gas that's closest to the element you're trying to write a configuration for, and you can plop its atomic symbol in little brackets and then continue from that noble gas. So for example, gold, remember we had like a million layers going on? Well, wait a second, 6s1, that doesn't even seem, I think this is not for gold. This might be a mistake that I did not catch. I'm gonna erase that. And we will configure and check this right now. But really what we would do is we go back to our periodic table. Let's say we were looking at gold again, right? Remember gold is number 79. Well, we're gonna look at the periodic table, the gas that is before that, which is xenon, Xe. So we write Xe in our brackets, and then we can check the rest of what I wrote there. After xenon, we should have 5s2, which I wrote, I hope. Of course, it's really small, and I can't read it now. Nope, I wrote it wrong. Good thing we're checking this. 5s2. Then we would have what? Got to flip between 2 minute tabs. All right, we would have 5s2. Then we would have 6s2. Jeez, sorry guys. Trying to flip between tabs. 6s2, 4f, 14. And then we would have 5d10 or 5d, maybe not 10. Let's see. 5d9 would be our final thing for gold. 5d9. 5d9. Okay. So hard to like type instead of write this. I'm like so used to writing. Great challenge for yourself there, Logan. So this is a shortcut that you can see and that you can use. So when you use the noble gas, then you really only have to figure out one row, maybe, of this instead of the entire thing. However, I would recommend practice writing out the whole thing, just so you understand, right? Unless it asks you specifically to do the noble gas thing, then maybe do that. Final thing that I will touch on here in the last few minutes of this session is you will see pictures like this in the quizzes for this class, right? These arrows represent the direction of the spin of the electrons. What you have to check on these is, do they have the right orbitals and energy levels? Right? They have 1s, 2s, 2p, 3s, 3p. That all sounds good. Like I said, the trickiest thing they'll do is they'll put 3d next instead of 4s. So they will put, this is not right necessarily on a question, check the orbitals. Do they have the right energy level and the right orbital listed? Then look at the spins. Remember, electrons will not pair up unless they have to. So notice in 3p, if you have 4 electrons, they do not pair up into 2 groups, right? These 2 will stay by themselves because they can. So electrons will only pair up when they have to. Okay, but that's a way that you will see this written out in the curriculum. We're not going to try that. The other thing I am going to say, because we got to end the session and we're going to review some of this stuff and go over some of this stuff next time as well, is that there are 2 rules for this that I want you to make sure you have written down, because they will be how you prove something, right? If you say, well, why is that true? Oh, because of the Aufbau principle, or because of Hund's rule, or because of this. So make sure you write these 2 dudes' names down. Of course, they're dudes. Aufbau and Hund. Right? And as you go through the lesson in Canvas, make sure you understand what their rule says and how it relates to what you just did. I wanted to make it a little harder where you had to actually figure this out on your own, right? Next time we will start by reviewing what these 2 rules are in next week's virtual session. Okay. Are there any questions about any of the stuff that we just did? Other than being like, it's a lot, right? But hopefully the shortcut will help you. I did record this video. So let's say you later are like, I don't remember how to do this, right? You can always click through part of the video and see specifically how to do something maybe that you missed or want to hear again. Otherwise, happy configuring, guys. And enjoy the break from the math, because the math's coming back after we talk about electrons. How were the layers named? That's a good question, Logan. I actually don't know. I think they're called S, P, D, and F because the name of the shape that they make, like S for sphere, P for something. Lane, no, we have not started bio. This is chemistry, so you're actually early. So you have 10 minutes until your class. So yeah, Logan, I'm not 100% sure, but I think it's based on the shape they make. I think they talk about that in the lesson. If I remember correctly, they do kind of talk more about the history. But yeah, you're right. It does kind of sound like programming computer talk. But I'm pretty sure it's based on the shape. Yeah, so again, check the lesson for that. I can look that up too and make sure that that is correct and let you know in the next virtual session for sure. But that's a great question. All right. Otherwise, just for being here today, you're going to get a code word, which is in the chat. You may use that code word to get 5 bonus points on any assignment or quiz or test or whatever, right? So especially like this electron configuration quiz is pretty hard. You can add your code word in the comments or in your question to get some additional points, right? You can also save your code word and use it later on a different quiz or test or on the final or whatever you'd like. So make sure you write that down somewhere and you note that that is a code word for bonus points. Otherwise, the assignment that's connected to this is the electron configuration quiz, right? But again, I would recommend you look through the lesson first, just to make sure that you're getting a little bit more background, a little bit more details, right, than what I gave you, because really my point here was shortcuts. I'm all about shortcuts. All right, otherwise, thank you guys for being here today, and I will see you next week, where we will talk about valence electrons and review a little bit of this stuff.